For centuries, scientists have debated a question that sounds almost philosophical. Is empty space truly empty? The answer is no. According to quantum mechanics, what appears to be empty space is actually a seething froth of virtual particles popping in and out of existence every fraction of a second. And now, researchers may have finally found observational proof of this phenomenon by studying a magnetar, a type of neutron star with the most powerful magnetic fields known to science. The discovery builds on a prediction made nearly 90 years ago by Werner Heisenberg in the field of quantum electrodynamics. Heisenberg and his team developed the Euler-Heisenberg Lagrangian, a mathematical framework that predicts that in the presence of an extremely strong magnetic field, virtual photons, the fleeting particles that spontaneously appear and disappear in empty space, can be converted into real, detectable photons. The problem has always been that the magnetic fields required to produce this effect are unimaginably strong. On Earth, even the most powerful magnets we can build are far too weak. But in the cosmos, nature has a way of outdoing human engineering. Magnetars are the cosmic champions of magnetism. Their magnetic fields are about 1 trillion times stronger than Earth's and roughly 1,000 times more powerful than those of ordinary neutron stars. When a magnetar flares, it releases more energy in a fraction of a second than the sun produces in tens of thousands of years. Data from high-energy space observatories, including NASA's High-Energy Astronomy Observatory and the Chandra X-ray Observatory, have revealed X-ray and gamma-ray emission patterns from magnetars that strongly match the predictions of the Euler-Heisenberg theory. The observed spectra show subtle features that can only be explained by the conversion of virtual photons into real ones. This is not just evidence for the theory. It is a direct window into the quantum structure of empty space itself. The quantum vacuum is not merely a theoretical construct. It is a physical entity that shapes the behavior of all particles and forces in the cosmos. Every time a particle moves through space, it interacts with this quantum foam, and the effects are measurable. One of the most fascinating consequences is its connection to the cosmological constant, the energy density of empty space that drives the accelerated expansion of the universe. In general relativity, Einstein included this constant as a way to make the universe static, a decision he later called his biggest mistake. But modern observations have shown that the universe is indeed accelerating, and the energy of the quantum vacuum may be the source. The connection between the incredibly small and the incredibly large is one of the most beautiful aspects of modern physics. Quantum electrodynamics, which governs the behavior of individual photons and electrons, has been tested in the extreme magnetic fields of a magnetar billions of kilometers away. The same theory that describes how lasers work and how atoms emit light is now being validated on a cosmic scale. This research also has implications for understanding the early universe. In the moments after the Big Bang, the universe was filled with an unimaginably dense plasma of particles and radiation. The quantum vacuum in those first fractions of a second behaved very differently, and the processes that governed virtual particle creation were far more energetic. By studying magnetars, physicists are running a laboratory experiment that recreates conditions similar to the early universe. The path from theoretical prediction to observational confirmation took nearly a century. Heisenberg and his colleagues published their theory in the late 1936. It took until the 1960s for neutron stars to be discovered, and nearly another 30 years before magnetars were identified as a distinct class of object in the 1990s. Only in the last decade have our space-based telescopes become sensitive enough to detect the subtle signatures of quantum vacuum effects. The study was conducted by an international team of researchers who analyzed data from multiple space-based observatories, combining observations across different energy ranges to build a comprehensive picture of the magnetar's emission spectrum. Their results were published in a peer-reviewed scientific journal, and the scientific community has responded with cautious optimism. What makes this discovery particularly exciting is that it opens the door to a new field of research. If we can use magnetars to study the quantum vacuum, we can potentially use them to test other predictions of quantum electrodynamics that have never been observed before. The universe is far stranger than we ever imagined. Empty space is in fact a vibrant, dynamic entity teeming with activity at the quantum level.